Hello, everyone, and welcome to my presentation. My name is Smail Kechidi, a KTB associate at the University of Leeds, and during the following minutes, I'm going to introduce you to the contribution of wood structural panels to racking capacity of cold form steel frames. This is part of an Innovate UK-supported knowledge transfer partnership between the University of Leeds and modular housing developer Ilka Homes. Just to give you a little bit of context, for the design of cold form steel structures, the Euro codes are usually available. However, for the development of a new wall system that would enable us to manufacture lighter, stronger, and more cost-effective structures, and even faster and with lower embodied energy, this is not currently covered by the Euro codes. In such situations, design assisted by testing and/or high-fidelity computational models is recommended. May be expensive for individual designs, but a super powerful tool in offsite mass production and manufacture. The approach we followed in our study comprises physical testing that aims to provide information necessary for designing and developing high-fidelity FEA models for cold form steel framed wall system, having or doing some virtual testing or computational analysis if you wish, optimization, and drafting some design guidelines. The outcome of these research activities would be reviewed to gain warranty and accreditation from the key reviewing bodies in the UK. As part of the experimental work, 32 steel tensile tests were completed, and the average yield stress at 0.2% offsite was determined to be 472 and 471 MPa for 1.6 and 2 mil thicknesses, respectively. This figure shows an example of test data. So raw test data was recorded as engineering stress and engineering strain, and therefore conversion to true stress and true plastic strain was carried out. In order to characterize the shear behavior of screws connecting OSB and CP boards to steel, 12 tests have been carried out. So the test investigated the sheathing type and thicknesses, as well as the distance between the screw longitudinal axis and the edge of the sheathing boards, what we usually call the edge distance. So here goes the test setup as built in the lab. And here go the results in terms of shear load versus displacement, as well as the typical failure modes witnessed during these tests of CP to steel assembly for different edge distances. We can see that the curves are comparable with an acceptable variation. We can see as well here that the edge distance parameter has no influence on the result in terms of shear force versus displacement, as the minimum allowable distance of from the edge required by the code was implemented. A similar trend was observed in the OSB-based specimens, and this result helped us in characterizing the shear behavior of this connection assembly to be implemented in FEA models. In terms of FEA modeling, ABAQUS software was adopted to develop a modeling protocol to be used as a virtual test bench for the development of a new CFS framed wall system for lateral stability of lightweight modular houses. The model and its parts are illustrated in this figure. The dimensions of the assembly are established according to the experimental setup we plan to adopt to test the developed new wall system, and cold form steel frame elements are modeled as shell elements, quadratic isoparametric shell elements with 9 nodes known as S9, R5 in ABAQUS. As depicted in this figure, a fine mesh is used in this study. Elements are placed at every 10 mil along the longitudinal axis of the cross section and 75 mil along the length of the OSB and CP boards. A material model using classical von Mises plasticity with isotropic hardening was selected for the steel, and as the parallel and perpendicular material properties for OSB are different, an orthotropic material model was used for OSB and an isotropic material was used for the CP board. In terms of modeling screw fasteners, although ABAQUS has a comprehensive library, elements are not yet available that allow for proper modeling of fastener behavior. To overcome this limitation, a user-defined extension to ABAQUS is made that incorporates empirical screw fastened connection behavior from test data. So recent research carried out by Ding resulted in an ABAQUS user-defined element, UEL, which incorporates the pinching form model and is capable of simulating strength and stiffness deterioration observed in response of screw fastened connections. To consider changes in vector force angle in ABAQUS analysis, a radial spring model is used for the UEL. Monitoring UEL output is very important in getting the simulation right, especially if the UEL spring results have significant influence on final results, as indeed is the case in cold form steel framed shear walls. As shown here, assessment of the shear force on screws at peak load capacity of the wall reveals that the screws at the vertical straight edges of the sheathing boards endure the largest forces, while the screws around the openings and in the top and bottom strips of the wall experience forces of lower amplitude. Similar trend was observed for walls with varying area, number, and position of the openings, as well as screw spacing. Here goes the demand to capacity ratio of screws at peak load capacity of the wall. This served as an optimization tool for designing the sheathing boards and screw layout to keep the screw density under the takt time of an automated high-speed panel line, which is 600 screws per cycle for one pair of walls that allows reaching Ilka Holmes production target. Having said that, a set of walls have been designed in terms of steel frame, sheathing, boards layout, and screw patterns. So here we consider the design in terms of stud cross sections and position, as well as the edge distance by considering a wider flange of the studs, and also vertical and lateral loads. In terms of the sheathing boards layout, we consider the minimum cuts just to save, just to have a minimum waste in terms of material, and also a better racking mechanisms. In terms of screw patterns, so the main governing criteria was wind load. So we considered wind loads to cover 80% of the country. Here, the country, I mean England. And also we had, as I mentioned a few minutes ago, we had to be under the takt time of the high-speed panel line, which is 600 screw per cycle. And we avoid to drive a screw in positions where double steel layers exist. So different wall typologies were designed in terms of openings as well. So here you can see that we designed this wall with a large window opening and a door opening. And here I'm showing a second typology of wall with a big door opening. And here I'm considering another wall with two large window openings. Just to have an idea about a solid wall behavior that is designed for areas in the in structure where openings are not do not exist. So here we designed two walls with without opening. So this is solid walls where similar design criteria in terms of steel frame, sheathing board layout, and screw pattern were applied. The lateral load versus displacement curves from monotonic tests on full-scale shear walls are plotted in figure in the left-hand figure along with FEA results. So the developed FEA modeling protocol accurately simulates the lateral behavior in terms of strength and stiffness of the tested walls. So the figure on the right-hand side shows the failure mode in the shear wall represented by damages in the OSB corners around the openings. A similar trend is observed from the FEA simulation, where the gray area in the von Mises stress contour show parts of the boards that are under stresses higher than their nominal strength, which is 7 MPa. Similar trend was obtained for the other shear wall topologies with different opening size and numbers. And here I'm showing the results in terms of load versus displacement, as well as failure mode of solid wall, where the failure mode was mainly the failure of the screws connecting CP to steel frame. To sum up, shear strength and stiffness provided by OSB and CP to steel screw fasteners in cold form steel shear walls have been assessed. Modeling of cold form steel shear walls with shell elements and discrete fasteners and their monotonic load is validated with test data. Evaluation of the demand to capacity ratio of the sheathing to steel screws at different levels of lateral load served as an optimization tool for designing the sheathing boards and screw layouts. The obtained results shed light on the capability of FEA to be used as a virtual test bench, particularly in offsite mass production and manufacture, for the development of a new cold form steel framed wall system for lateral stability of lightweight modular houses. This has enabled Ilke Homes to manufacture lighter, stronger, and more cost-effective modular houses even faster and with lowered embodied energy. And thank you for your attention.